Great, thanks very much. You've seen the title, and you've seen it needs a question mark, and part of the purpose of the talk is the question mark. So, thermodynamics, Einstein. Thermodynamics is the only physical theory of universal content which, within the framework of the applicability of its basic concepts, I'm convinced will never be overthrown. Eddington, the law that entropy always increases holds, I think, the supreme position amongst the laws of physics. If someone points out to you that your pet theory that the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it's found to be contradicted by observations, well, these experimentalists do bungle things from time to time. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So we have this law which has effectively creedal status, universally accepted as creedal status, yes? But it has to be one of the most misunderstood and abused laws in science because people don't understand it. So if you have any off-the-wall crackpot idea, the second law gets a mention. Why does time go forwards? Well, the second law requires irreversibility. So the second law forces time to only go forwards. There you are. So any off-the-wall idea, you just cite the second law, right? That's basically it. So a complete abuse of one of the most useful things in science. The point is, if you have any scientific investigation, at some point you can say, but that's thermodynamics, so that has to be true. It gives you an absolute fixed reference point in a discussion of what's going on. Complete, absolute fixed reference point, of which this is the only one. Now, it's very interesting, a few years ago, in about 2011, some people measured the speed of light of neutrinos. And many of you remember this, and they measured it went faster than the speed of light. Now, everyone quietly thought, well, I doubt it somehow. But no one said it cannot be. The sacred cow was about to go, or could be on the altar. And no one said it can't go, because they knew it could. But that is not true of the second law of thermodynamics, basically. It's quite extraordinary. At least that is the universal perception. So the question now is, what on earth is this law? And how on earth do you have something which is that certain that people like Einstein will put their shirt on it? Now, the Maxwell's demon problem illustrates many things, not least the complete confusion surrounding by subject. Because he proposed something in 1860 or something which has not been satisfactorily explained. And the current explanation, as we'll come to at the end, is complete and utter gibberish. Yet it is produced in all the textbooks. It is stunning. It is stunningly bad. And that illustrates the problem you've got, that you've got this beautiful theory which is completely and utterly mangled. And so the idea of this talk is to address the Maxwell demon problem and hopefully on the way shed some light on what's going on. Okay, now the first thing is, what is thermodynamics about? Now, thermodynamics was invented by people like Carnot to handle steam engines. It's about dynamics, thermodynamics. It's about change. Now, the interesting thing about science in the universe is not statics, it's change. What we want to know is how things change. Thermodynamics is about change. Okay? So, for example, take the water cycle, and if I can work out how to turn this thing on. Pass. Oh, wow, that works good. Okay. So the water cycle, millions of processes, all of these are change. And what more can we say about them? Well, all change on the macro scale is driven by dissipation. All right, this is a central thing about how the universe works. All change on the macro scale is driven by dissipation. I'll talk about that for a few minutes and hopefully convince you. The point is the constituent particles spread, and where they go is what they do. And all we've done, or what nature does, is it controls it from outside, okay? There's a hillside that the water flows down, so the water flows down the hillside. But the hillside doesn't actually get individually at the particles, they sort of talk to each other and sort themselves out. Now, the point is that when change stops, we have equilibrium. Now, much of thermodynamics' use is in equilibrium thermodynamics, chemical equilibrium. But that is just the very special case when the change is stopped. The subject itself is about change, not equilibrium. That's just, you can use it when change is stopped as well. Okay, so that's a minor use of the subject, really. And if you consider equilibrium, it's comparatively boring compared to this, right? Yeah? Now, let's talk about change then. Now, let's think about an archetypal change. How do things change? Well, okay, a good archetypal change is that of a gas expansion. So imagine a box with a partition, the gas on one side. The simplest sort of change you can imagine is you take the partition out and the gas fills the box, right? Now, that is irreversible because if you put the partition back in, the gas doesn't go back, right? So that's an irreversible change. But you say, I can just push it back. Okay, let's try. So we'll set up something to push it back, take the partition out, whip it out, bang, it fills the gas, and then you allow the weight to fall and compresses the gas. So the gas, now, you know if you pump up a bike tire, it gets hot. So the work done by the weight in pushing the gas back becomes heat. That's dissipated. So yes, the gas has gone back to where it was, but the weight has fallen. The rest of the universe is in a different place. You say, okay, well, let's lift the weight up. Well, how are you going to lift the weight up? Well, let's have another weight. That falls and lifts it up. Well, that doesn't gain you anything, does it? Well, let's have something else, like a steam engine, which dissipates to lift the weight. The point is, once a change has occurred, it cannot be undone. The universe cannot go back. Once you've taken that partition way out, there is no way of returning the universe to the situation it was before it happened. So every time anything changes anywhere in the universe, it's irreversible, and you cannot take it back. This means the universe is like a firework. It's a single-use object. You assemble the thing, you light the blue touch paper, and it does its stuff. It starts off with go in it, and the go is the fact it's all in one place in a tiny volume at very high temperature, and it then dissipates. And it's a one-way firework, and it is extremely hard to consider logically and reasonably, therefore, how it does not have an origin, which means either it has no cause or it comes from somewhere which doesn't obey our rules. And that has to be the most fundamental philosophical conclusion of science, and it's based on the one law, which everyone agrees is inviolable. Now, so there's a lot at stake in this. Enter Maxwell. So Maxwell then comes along and says, I've got a scheme, and I think this scheme will bust this. And this is what this is about. Can you bust the second law? And what he said, well, suppose you have a demon, and he said in a finite being, the name demon was coined later, a finite being which sits here and watches the molecules. So you have a partition, trapdoor, two detectors. Supposing it detects a particle this way, going fast, open the trapdoor, let it through. This way, going slow, open the trapdoor, let it through. So the cold one ends up here, the hot ones end up there, and you end up with a system which is heat flowing from cold to hot. Or you could do it more simply. You just open the trapdoor. If one is approaching like this, shut it when it's not, and they all end up on the other side. Job done, second law violated, okay? So that is Maxwell's demon problem. Can something, an intelligent being, some machine that watches it, sort them and bust the whole thing? So that's what it's about, okay? Now, if you want to understand the nitty-gritty of that, you have to understand a bit more about thermodynamics. So for the next bit, I'm going to talk a bit about thermodynamics, then return to that at the end and see why you can't bust it, all right? Okay, so let's consider the anatomy of change. How does change occur? Well, you can imagine before something changes, it's just sitting there. And so if it's in fluctuation, it's at some sort of equilibrium, and the particles are held there by a constraint. Now, the change is initiated by changing the constraint. You make a hole in the wall. At that point, the particles can start to respond, and by themselves, they wander around, some of them go through the thing, and they dissipate. Now, if this is done slowly, then what you can do is you can track the change. You can say, on average, at a certain time, how many on this side, how many on that side, so the change can be tracked. Now, if it goes fast, you could still track it by repeating it 1 million times and taking averages, couldn't you? So a change can be tracked, all right? This becomes important later, until they end up equally distributed. So of course then, you don't get 50-50 mixture, there's a distribution. And anyone who knows any statistics will realize the deviation is about root n. So basically, if you look at this thing, you'd expect to see 40 one side, 60 on the other. So it sits there and changes, it fluctuates. So if you have the numbers changing by small amounts, we call it fluctuation, because it goes backwards and forwards. But what you don't get is them all returning to one side. Well, you could, And the chance of that happening is 1 in 10 to the minus 30 compared to that. So let's put a number on that. So we call that fluctuation, because it's quite likely. And that, because it's monumentally unlikely to go back, we call a change. All right? Now, to put a number on that, supposing you had 2 litre objects, 100 atoms each, thermal velocities, big hole between them, about 1,000,000 times a second, the number on each side changes. How long would you have to wait till you had a decent chance they're all back on the first side? Answer, 200,000 times the age of the universe, and that's just 100 atoms. Okay? So that's what we mean by unlikely, and that's what we mean by change. Okay? So change is monumentally unlikely, and fluctuation is likely. Okay? Right. Hang on, you say. But I just push fluids down a pipe. No distribution is involved. No, wrong. If you move a piston, it squashes the stuff next to the piston. But then the actual motion of the fluid is as that disturbance dissipates, isn't it? Yes? All right? Now, we just had a whole lecture on astronomy, so I don't need to say anything about dissipation in astronomy. I was going to talk about tides and synchronous moons, about orbits, which are made circular by gravitational force, about Io, dear little thing, which is fried by Jupiter. That's already been covered beautifully. That's all dissipation. The point is nothing is rigid enough. If you're made of particles, nothing is rigid enough not to be involved in dissipation. That's the point, you see. Yes? So everything can dissipate because it's just not rigid enough to get around this. So let's take another example. So you say, well, hang on, guys. I did O-level GCSE. Actually, I did O-level, but GCSE physics. Let's take a pulley system. So we have a pulley system. We have 2 weights and a pulley. So you say, look, come on, get real. Pulley, weight, weight. You apply a small force, they start moving. Small force, and they stop. Now that is completely reversible. What on earth are you talking about? Well, I'm talking about the real world, not GCSE. The real world, this pulley is surrounded by molecules. All right? And if you're going to propose a friction-free pulley, they're doing Brownian motion. So they jiggle. So you move them in the right place, they go away and make a cup of coffee, and you come back and they're in a different place. They've moved, they've diffused. Now, if you want to stop so that you haven't achieved anything, you have not achieved a well-defined change. If you put it in a certain position, you turn away and it's gone, it's moved somewhere else. You haven't achieved a defined result. Do you see, yes, right? The result is not defined because it's just diffusing. You know, a speck of dust in the atmosphere, although at a point in time is at a particular place, but it's not a result, it's not change which just sits there unchanged, right? So what you need is, normally this doesn't happen, of course, you have friction. So what you need is a brake. So you say, look, you're still wrong. I've got my pulleys. All I have to do is slide a brake onto the pulley, and then it can't move. Sussed. Yeah, but the brake does Brownian motion, doesn't it? So sooner or later, you have to have something which is located. All right? If you want something, a change which holds, it has to be located. Now, the only way to locate it is a potential barrier to stop the motion, stop the diffusion. So this is how a switch works. So you have a switch, and it's located because there's a barrier. So you take the switch and you push it, and you do work on it. And then it goes click. So the switch gets to the top, and you've pushed it up there, and then at that point, it falls down the other side, and all that lovely potential energy that you put in as work converts to K and is dissipated as heat and sound. Now the point is that the heat is dissipated, so it doesn't all come back together and push the thing back over, does it? Now you could say, I can get around this. What I'll do is I'll put a spring. So as it goes over, it compresses the spring. Fine, you store the energy. The spring promptly pushes it back. All right? So the only way to get a defined result is to have a dissipation. And if you want to hold something in position, you need a barrier which has to be surmounted by dissipation to get a defined result. Okay. Now this at the back of it, remember, we defined change as a defined result. So you would say, well, no, that was our definition of change as a defined result, yes? Okay, that's what we meant by change, okay? So if something is in circular orbit, that's not changing, it's just doing circular orbit. Do you see, yeah? Right. Change is when you change. Okay, now. So that's the background to this. Now, the basic point, of course, is nature is hierarchical. We observe things on one scale. They're caused by objects moving on another. There are too many objects to keep track of, so we want to describe it in terms of headline variables. And this is the trick. And the way We want to describe this, basically, yeah? And so the basic trick is you have some sort of local equilibrium. So take a box of gas, fill it with gas, and wait. And once the pressure has settled down, the temperature has settled down, you can describe the gas inside in terms of temperature, pressure, and density. Yes, but you have to wait till you get equilibrium. Yes? So the basic trick of thermodynamics is you have to wait for equilibrium before you can use these variables. But you can divide the world up into tiny boxes. Yes? And so all you need is equilibrium within a tiny box. Yes? So you can have, like, temperature can vary through a room. All right? Now, that means, therefore, you can use thermodynamic variables to describe explosions and shock waves beautifully. That's fine. Because if you do a simulation, for example, and you take gas molecules, you start them all off going at the same speed, it takes just 4 collisions to establish a decent velocity distribution. Now, that means it happens in less than a nanosecond. So local equilibrium in a gas, in a STP, is established in less than a nanosecond. That's how long it takes, which is why you can do explosions, yes? Okay, because that's ages on this time scale, yes? Local equilibrium is established, so you can use these variables. Now, again, why does this trick work? The trick works because the time scales that we're interested in are huge. So at one end, you have quark-gluon plasma slammed 2 lead nuclei together in the LHC, and that thing comes to equilibrium in about that sort of length of time. The other end, you have clusters of galaxies, and I've seen at least JRF applications where you have a cluster of galaxies. So the particles is a whole galaxy, right? That's one particle. You have a cluster of these, and you talk about relaxation of the galaxy, which takes place on so many billions of years, yes? So it's quite a right timescale. So if you just pick a timescale, any number, pick a number. So, for example, we'll be there. Then the chance of you hitting something is 0. Because it's all either faster or slower because the timescale is so big. If you're really unlucky and you hit something, all you have to do is move the timescale a teeny bit and go one way or another. So either it's changing or it ain't. Yes? And therefore, you either say it's static, like, for example, if you mix hydrogen, oxygen, and gas, they quickly interfuse, but they don't react. So the reaction is on timescale you can ignore, but the interfusion one is fast. So you're always in a situation where either it's not happening or it's happening fast enough, you can use the trick, which is why it's so powerful. Okay? Right. Now, let's think about this. Supposing you can have a series of events. Events are not just one-off, but they can be part of a chain of events. So let's suppose you have a box and with lots of water around it to keep things at a certain temperature, and you start off with 10 moles of electrons, 2 of hydrogen, of protons, and 1 mole of oxygen, plasma, right? Now, they can form atoms, dissipate buckets of heat. They can form molecules, dissipate buckets of heat, and they can react to form water. Now, if this thing is sitting surrounded by a tank of water, this is a one-way process, isn't it? Yes? Because you put in any of those stages and it can go to the right. Yes? All right? So there's a chain. So you can start with this, but can you see that as you go along, the thing is progressing along the path? And the question is, what you'd like is some measure of how far down that path it's gone. And this is what entropy does for you. It measures how far the dissipation has proceeded. This experiment is also quite nice, because actually what's happening here is assembly. You are assembling the water, aren't you? This is not dissipation of the molecules, is it? It's assembly. So how is this happening? Well, the answer is because it's dissipating heat. And the point is you can trade off dissipation of one thing against assembly of the other, which is also why it helps to have some variable, some number you can put on it. What's the currency? Can I trade off this dissipation against that? You want some number to quantify it. This is what entropy does for you. Now, but the trick here is, you see, is that, for example, suppose you take this mixture, and suppose you put it in the box, and you put the box at 100,000 Kelvin, in the middle of a star. They don't assemble. Reason? Because you can't dissipate the heat. They can only assemble by dissipating heat. And if you stop them dissipating the heat, they don't assemble. Right? So the dissipation of heat is intrinsic. To be able to dissipate something is what allows you to assemble something. Okay? But there has to be net dissipation overall. Okay. Now let's take another case. Supposing we have liquid water, like water in a vacuum. Now, of course, the liquid can dissipate by evaporating, but to do so, you require latent heat. So heat has to assemble. So as that dissipates, heat is assembled. until you get to a point where the amount of dissipation gained by extra molecules going up is exactly balanced by the going the other way and get equilibrium, yes? So the whole thing is about dissipation, it's about balancing dissipation, it's about how do you quantify dissipation in order to describe the whole process. This is what the whole thing is about. So that leads us to the laws of thermodynamics. The basic one we've already had, which is that we're going to use state variables, assumes an equilibrium. What that means then is, you see, the glory of this is the thing takes care of itself. You just put a box, you define the conserved quantities. You say, right, what are the conserved quantities? We've got so much volume, so many particles, and so much energy. And you leave it be, and then it sorts itself out. So if you've got some water, to vacuum, put water in, just leave it be. Come back later, and there'll be an equilibrium between water vapor and water. It sets itself up. You don't have to set it up. You specify the conserved quantities, and it sorts itself out. That is central to this, which is why it's so powerful. Because you don't have to worry about setting it up. It'll do it for itself, because it finds the right thing. All you have to know is the conserved quantities, and it will do the rest. Okay? So that makes this thing very powerful. Now the laws, first law, or zeroth law, because people forgot about this one, temperature, if A is in thermal equilibrium between B and C, you know without testing that B and C will be in thermal equilibrium. There is a state variable called temperature, which is so blindingly obvious, that's why they didn't bother to do it, and someone stuck it in later. Energy was a bit more significant because people realized since time immemorial that energy wasn't conserved, but then they realized it was if you had included heat, courtesy of Joule and cannon boring and things like this. And this is written in terms of internal energy, heat transfer, and work done. Then we get on to the second law, which is where the fun starts. Now, the second law first came up with a chap called Carnot. We'll talk a bit about him in a minute. But basically, Kelvin and Clausius rediscovered Carnot's work. This chap Carnot, he was a French military engineer, and he worried about steam engines. 1824, wrote a publication on the motivation power of fire, except it was in French. And he, before anyone had thought about atomic theory, they thought heat was calorific, they knew zero. Just before Dalton, he comes up with the second law and derives some of the key things about second law, which is pretty amazing. Okay? Now, his work was promptly forgotten, right? And these two gentlemen discovered it about 30 years later, separately in different places. But he didn't have the internet in those days, so you could forget it. What's worse, he wrote it in French, and even worse, he started off by praising the British engineers for their expertise in building steam engines. And this is written in France in 1824. I think it went down a bit like a lead brick. Okay? So, if you want to write a good paper, don't go and praise the people who've just annihilated your country. Okay, so Clausius, there is no possible process whose solely effect is transfer heat from a colder body to a hot body. All right? Kelvin, no process is possible whose only effect is the complete conversion of heat to work. Learned for your exams. Now, what this one is saying is you can't sit in the middle of the North Atlantic and drive your ship by taking the energy out of the seawater. And what that one is saying, if you have a fridge, it'll only work if you have a power supply. Okay? Now, you can put these more simply, which is the heat flows from hot to cold. They're just complicated ways of seeing heat flows to hot to cold. And you say, well, isn't that tautology? And the answer is no. It's just something we're very used to. What it's saying is you take two bodies and you determine the direction of heat flow. You then take a whole string of other bodies and make them the same temperature as those two, and without trying it, you know that heat will flow from that direction only. Yeah? Now, to us, that is so obvious. We think it's a tautology, but it's not. That's what the law says. You says you can't do that. All right? Unaided, heat does not flow from hot to hot, cold to hot. And perhaps you begin to see why no one is thinking of busting this law anytime soon. Okay, all right? Yes? Heat flows from hot to cold. That's what it says. It also says averages converge to the mean, if you think about it. All right? Now, so let's generalize this from heat, because we've already seen that it's not just heat, but particles that can flow. So they were talking about this, hot, cold, they end up warm, and we've had this. Now, you can show that if this could be violated, it would bust that. And so actually, this is second law applies to all irreversible processes. So you can have different statements, which are perhaps more general. Direction of an irreversible process and the nature of equilibrium are determined by the state of the system. So take two systems, and which way the heat goes depends on their state when they start, which is hot and which is cold. That determines what happens when you put them together. Take two gases like this and put a partition. One that has the higher pressure is the one where the gas leaves. It's determined before you try it, okay, by the state of the system. Another definition could be multi-particle systems, as described by state functions, and in a state of flux, show irreversible processes. Yeah? Or you could quote Theresa May. In the absence of external intervention, irreversible means irreversible. Yeah? But that's actually what the second law says, is that if something is irreversible, it's irreversible. Okay? Good. Right. So what can happen and what drives it is determined by the start and end states of the system. This, of course, makes matter a lot easier, because how things change is furiously complicated. How fast things change is furiously complicated. But it's a lot simpler to say what the state is. But what happens, what can happen, is determined by the state of the system. You don't have to worry how it can be achieved. Now, why does this work? Why does this work? Remember, we're talking about the law, which governs irreversibility. Why? Okay, let's think of a case and see why it works. So take a box. All good things in thermodynamics go to a box of gas. So what you do is take a box, now you take three of them, and you take two holes of different sizes, yeah? And we know they come to the same pressure. The question is why? Because if you can understand that, you can understand the second law, can't you? Yeah? So let's try and work out why it is that the gases come to the same thing. Well, the answer is because of time irreversibility. The second law is contingent, actually, on time irreversibility. Okay? So how does this work then? What is time irreversibility? So someone takes a cine film of nature on the atomic level, and they hand you the film. And so all you've got is the film. The question is, which way do you play it? And the answer is you can't tell, because playing the cine film in either direction obeys the laws of physics on the fundamental level. Right? That's time irreversibility. So let's take this thing. Now, the first thing you realize is then that for every forward propagating state, there has to be an identical backward one. So if you can identify something about the system which is traveling forwards, it has to have a precisely equal thing which is going backwards. Otherwise, you could work out which way to run the cine film, couldn't you? By just looking for the absence of the states. So every forward propagating state has to have an exactly equivalent backward propagating one. Furthermore, if you change a constraint, like you change the size of the hole, you have to change them both in the same way, don't you? Otherwise, you could tell which way to run the film. So if you make the hole bigger, the forward one has to increase by exactly the same rate as the backward one increases. Otherwise, you know which way to run the film. So therefore, there is nothing you can do which changes the relative rates of the forward and backward reactions. Therefore, what's going to win is determined by the state, because whatever you do to the kinetics can't change what happens if you're doing something passive. Now, if you move something like a pump or a fridge, then that is not bound by time reversibility, because you can push it in one direction, do you see? So that can wreck this, yes? But if you've got passive constraints which are not moving, you can't bust this, all right? So the whole thing is based on time reversibility. Now, to illustrate that, let's take a case where time reversibility doesn't work. And a good case is motion in a rotating system. So if you throw a ball on the Earth's surface, then it follows a curved path due to correlative forces. If you then try and throw it backwards, it doesn't retrace its steps. Now, if you bother to do the job properly and change the direction of the rotation of the Earth, it would. But if you forget to do that, it doesn't, okay? All right, so we have a system which breaks time reversibility. Let's see what happens. Now, you imagine a straight pipe with two vessels. Imagine the North Pole in the middle. So it works anywhere in either hemisphere, just rather best at the North Pole. And of course, by symmetry, if it's like that, the rate of passage in the two directions has to be the same. But what happens if you put a curved path between them? Well, let's look at some trajectories. And you can see this curve, the trajectories are all curved. So imagine things starting at a point that collides with the wall and hits. We're imagining the pressure is so low it just hits the wall. So it hits the wall, and you can see that if you go from straight to curved, if it's hit that wall, the ones going in that direction are suppressed, and the one in that direction is increased. If you start the other side, well, the jury's out. Some in that are compressed, and this you're not quite sure. So you do a simulation. You can start lots of trajectories in different places, and this is just one trajectory, and you can see, sure enough, they bunch up at one end, because there is a net effect. Because if it's curved, if you've got a curved trajectory going with the curve, it goes an awful long way. Whereas if it's going the other way, it sort of hits the wall super quick. So you diffuse is faster one way down the pipe than the other. So this then ends up with a density distribution which is higher at one end, and so if you have it that way around, that's low, that's high pressure. If it's straight, you get medium. It's the other way around, so you just bust the second law. Because the state of the system, whether you have high and low pressure, depends on how you connect them. So if you bust time reversibility, you bust the second law. Okay? So that's just an illustration. Now you ask, well, what's going on? Well, actually, of course, it's just a pump. So there's also a thing called CPT, that actually there are rare processes which break time reversibility, and you actually have to reverse the time. You have to reflect the whole thing in the origin, you have to change the sign of the charge. Now, reflecting everything with the origin is quite good, because that will reverse the rotation of everything, won't it? Yeah, so you can understand that one. Why you have to go plus to minus, ask a high-energy physicist. But you wonder if there's something moving that we haven't reckoned on. Okay. Lerschmidt's paradox. This is a good one. How can irreversible behavior result from basic physics that obey time reversibility? And you can imagine the acres of print and text which have been expended on this one over the years. Wonderful conundrum. Well, the reason is, so the problem is, why, when you put the partition back, doesn't it all go back? Well, you think, you've got to be out of your tiny little mind. And the point is, when you change the constraint, when you put the partition back, you don't reverse all the trajectories, do you? Yes? So the point is, when you do this sort of, you change the outer conditions, don't you? And so, but you don't change the direction of the propagation of the molecules. So why on earth do you expect it to go back? It's just nonsense. So that's why you get Lerschmidt's paradox, because you don't change it. Now sometimes, if you make a halfway decent attempt at reversing the trajectories, it does go back. So here we are, light being scattered from a person, looks pretty hopeless, yes? Until you put a lens in front of it. Now what the lens does is it reverses the lateral velocity, and sure enough, they all go back. So if you make a halfway decent attempt at reversing the particle velocities, they all go back pretty well. And how well they go back depends on how hard you try. So if you do a spin echo experiment, you can run the spins forward and backwards. Now these are sometimes cited as breaking the second law, but they're not. The point is, for once in your life, you've actually tried to reverse the velocities, and so of course it goes back. Yes, so that's Lerschmidt's paradox. Now this raises, if you put a ground glass screen in, then that messes up the velocities, and so you can't send them back. Now this raises the interesting question of when does the irreversibility occur? All right, cue more acres of print. Now supposing you have a small box with a hole. You open the hole and the things come flying out. Now when you're in this sort of state, you look at it and you think, well, probably you could work out how to send them back, couldn't you? Not easy, but not beyond the bounds of probability, yes? Okay? But once they hit the wall, you say, no. That's beyond it. Bridge too far, yes? Now, the point is, the irreversible step occurs when we decide we've given up. Yeah? Because we're the ones writing the equations. Now, nature does what nature does. It couldn't care a fig about what we think about it or what equations we realize, yes? But if we choose to describe it in terms of a particular scheme, then the way we describe it has consequences. And if we give up, then we've given up. Now, there can be a very good reason why you give up, but at the end of the day, it's that cool that this is, and the question is, the only reason why you would want to keep the possibility of going back in is if you could think of a way of doing it, yes? Otherwise, there's no point in keeping the possibility of going back in your description, is there, yes? So ultimately, we make the call, but it's often, our hand is forced. There's not much choice, really. So the second law. So now I just need to speed up a bit on the maths, and we'll quick maths bit, then we come back to no maths. So apologies, maths. Okay, now Carnot, this guy, there you are, June 1824, wrote this thing, and he was worried about the efficiency of a heat engine. He proposed an ideal engine, hot like the boiler of a steam engine, cold like the condenser. Heat flows out the boiler, some of it goes back. Well, he didn't say this, but this is what you do in the modern thing. He thought of heat flowing from hot to cold, like water in a water mill. High level of water, low level of water, heat flowing. That's what he imagined, because he didn't know heat could be converted to work. So he imagined it flowing. And so he considered this situation, showed various interesting things. When Clausius rediscovered his work, he took it a bit further, And actually, because he knew a bit more about thermodynamics, like conservation of energy, he could work out the heat and the work. And he showed that if you have a reversible engine where all the steps can actually be put backwards, which actually gives you the most work out, then the key equation was the heat flowing out of the top divided by the top temperature, when you're at optimum conditions, is the same as the heat flowing out of the bottom divided by the bottom temperature. So this is quite a sort of quirky sort of thing. Now, this one is big and that's one small, and the difference gives you the work. So from that, you can work out the efficiency of a fridge and things. Now, this is heat in, heat out. Oh, physicists hate that. Make them both heat in. So change the sign of that one. So that means the sum of the heat transferred irreversibly divided by temperature is 0, and you can generalize from that to any old system and have an integral, which means, therefore, since if you integrate something around a loop and get back to where you started, like potential energy, then what you've got is a function of state. So there is a function of state given by dq upon t, and furthermore, by considering these engines, they showed it always rises. So that's how entropy is defined. Completely bizarre. You take a system, you do a change reversibly, measure the heat transfer, divide by temperature, that gives you the change in entropy, yes? Clear as mud. But that is what it is, and it has this magical property that it always increases or stays the same. What on earth have we done? Okay. Now, this was addressed at various stages, firstly by Boltzmann, and he produced arguments to say the following. If you think of the number of states that your system can explore, that's omega, he showed, or came up with the idea, with some sort of arguments to back it up, that the entropy was some constant, Boltzmann's constant, times the log of the number of states. So he came up with that, and this is called the Boltzmann definition of entropy, which is what most people quote if they quote the definition in statistical mechanics. Now, he had immense difficulty, as you may know, of persuading the people around him that this was correct. Now, the first problem was not because there's anything wrong with his arguments, but the fact that the dear old physicist establishment at the time did not believe the world was made of atoms. So you have, 50 years later, the chemists, Dalton, are doing periodic tables and combining ratios and et cetera, gases and all the rest of it. And the physicists have their head in the sand, and they're saying, no, I don't believe it. I have to see it with my own 2 eyes, you know. So they make complete and utter fools of themselves, but they hold the moral high ground and won't believe it. So this is his basic problem. So he goes off and studies philosophy in an attempt to try and work out how to persuade these recalcitrant idiots to open their minds. But the problem is that great advances in science generally work by the old scientists dying, not by the old scientists changing their minds. There are very, very few scientists in history that have ever changed their minds, one of which was Joule, famously. But by and large, new ideas propagate by new people coming on, which is a bit sad. Anyway, that was his trouble. That was his first problem. He even said, why don't we just accept this as a hypothesis? Come on, guys. Okay, I know you don't believe it, but why don't we just treat it as a model that works? Because it does give the right results. No, won't have that. Okay. After all, that's what all science is, isn't it? All science is just a model of what's happening. That's all we ever have. And that's what he proposed. But, oh, no, that wouldn't do. Anyway, the second problem was his formula is wrong. And the reason why you cannot prove that that formula is the correct definition of entropy is because it isn't. And if you try and prove something mathematically which isn't the case, you have extreme difficulty. All right? Which is why all the thermodynamics books don't prove it, and why they say, oh, just assume it's the case and then see what happens. Okay? The third problem is there are lots of different definitions of entropy in statistical mechanics. And the problem is the numbers are so big that to turn them into useful numbers, you take their logs and then you multiply by 10 to the minus 23. And if you get it slightly wrong, it doesn't make a blind bit of difference, because the difference between all these things is 1 part in 10 to the 23. So basically, you can have any tin pot, crackpot idea you like of what this thing is, and it'll work. Right? So that's a problem. Okay, so there is a correct answer, which dear old Gibbs came up with, and in a minute we will look where that came from. Okay, entropy. So to do this, then, we have to look at microstates and microstates. So microstate is what we've actually got. You imagine lots of little boxes where they are, fine. Now, let's think about spreading. So if we have a system and a piston, as the piston moves out, the system spreads over more states. and we can work out how the number of states changes. But as it spreads, the molecules bounce off the piston and cool, so the gas cools. That means if you want to keep the temperature, you have to put heat in. So you can work out how to relate how the extra number of states compared to the heat you have to put in, do a bit of maths. Sure enough, you get that. All right? Now the point is that if these are moving fast, the change in energy is a lot for a small change in velocity. So you have to take the energy change and scale it by the kinetic energy to convert it to the number of states, which is why this formula sort of works. Now, that actually is a special case. This is at thermal equilibrium, and it's isolated, in which case that's the correct expression. Now, okay, so dissipation and work. Now, the point is, everything is driven by dissipation, and for the world to work, what you need is something to dissipate. This is what sunlight does for us. It comes in, high energy photons, energy concentrated, and can be dissipated. This is what coal has. It's not the energy it's got, it's the something that can be dissipated. And that's actually what we're interested in, okay? So let's get the correct formula. Well, people who know thermodynamics have seen all this. You have to define temperature, you have to define a Boltzmann factor. And then what you need is the correct circumstances. Now, the correct circumstances for entropy is connected to a heat bath. Classical entropy is only defined for systems connected to a heat bath. If you disconnect the system, it is no longer defined. Okay? You have to have it connected, which means you want the difference in energy before and after the change. The energy is the average of state energy times that, so you can work that through and see how it changes, use your Boltzmann factor, and you end up with that's the correct interpretation, because it's fluctuating before, it's fluctuating after, so you have to average over probabilities. And that then is the correct expression for entropy. Now, this is the average value of the log of the probability. Now, if you exponentiate that, you get this thing. Now, what is that? Well, suppose you have a state, you can be in 1 or 2, and every time you see it 1, you write down its probability. Then work out the geometric average of those numbers. That's what that is. This is the log of the geometric mean of the probability, except it's the geometric mean as so you see it. What it is, it's the log of, it's the effective probability of the state. Probabilities are used multiplicatively, so you want the effective multiplicative effect of your probability, and that's what this thing gives you. That's what it gives you. Now, if you look at this thing, now supposing you have a system, starts off like this, you take the thing away. The point is, during the change, local equilibrium is established. So you can have non-equilibrium values of the probability, but you can still work out what they are, right? Because locally it's sampling your states. So you can have probabilities which are not equilibrium ones because the change is underway. And therefore you can use this, and this thing has the property that it always rises. So you have a mathematical function which always rises as the probability converges, which is why that converges. And this works in these cases. And the point is, this thing works under all circumstances. But classical entropy was defined under very special ones, because accidentally, under very special circumstances, namely heat transfer to something in equilibrium, under those very special circumstances, you can actually access this function in terms of macroscopic measurements. But the thing itself is actually universal. So that's what entropy is. And now, if we probably ought to get back onto Maxwell's demon. So, back to Maxwell's demon. This is the fun bit. So, got the proposal. And what's the answer? The answer is the traditional answer, which is that if you want to measure the positions, if you consider any process which measures something, for example, a photon comes in and is scattered. You put a detector, photons coming in. If it doesn't arrive, you know there was something there. And that's because it's scattered, yes? So scattering is dissipation, yes? So any conceivable process for measuring actually involves dissipation, just because you can show it. That's the first reason. The second reason is you've got the trapdoor, and the trapdoor needs to be located. The trapdoor is like a switch. So if you have to, so when you move the trapdoor, it's like moving a switch. It has to be in a defined position, otherwise you can't control it. So therefore there has to be a barrier that you push it over, all right? And that's where you lose the entropy. So, and this goes back to the fact that any defined result is a result of an irreversible change. If you measure something, it's a defined result. If you move a trapdoor, it's a defined result. So that's why it works, okay? Completely covered by everything as previously. So what is interesting about this? What's interesting about this is the complete and utter dog's dinner which has been made of it, so which has to be seen to be believed. Okay, so this is the explanation you'll find in any thermodynamics textbook. This is what you find on Wikipedia, except Wikipedia is a bit more upfront than your average textbook, bless Wikipedia. So it's all about information. Okay, so the statement, it turns out you can measure position without increasing entropy. Well, that's wrong. And if you look at the method, they say, well, here's a way of doing it, but it requires things to be located, so it doesn't work. So what they prove as the example for how you measure things without dissipation gives dissipation. Never mind. Okay. Second statement, it's all about information. Well, Shannon did talk about information and came up with entropy. And you can do processes where information isn't lost. You start off with 10 numbers, and you do process, and you end up with 10 numbers. So you can work back, so it's reversible. Fine. But we're not talking about information. We're talking about real things. Those numbers are represented by physical entities. We're not worried about the maths. We're worried about the physical entities which represent them, and they have to be moved around, right? Defined results. It's not all about information, despite what they say. The daemon needs memory to remember what it's done. So they're thinking of a computer. No, it doesn't. Why does the daemon need memory? Well, they say you need to remember where the trapdoor is. So what you do is the daemon writes down on a piece of paper, the trapdoor is in position 1. So if he wants to know where the daemon is, it looks on the piece of paper and says, oh, it's in position 1. Why doesn't it look at the trapdoor? You don't need to record where the trapdoor is. It's its only memory. You don't need to record where the trapdoor is. Never mind. Onwards and upwards. So storing information is not a problem. Rubbish, it is, because you have to change things. Eventually it runs out of memory. Yes, it will. And it needs to wipe some. Yes. And then comes the beauty. In order for the second law to be held, at this point, because we've reached the end of the road, something must happen which generates entropy. Because if it doesn't, the second law will be violated. Right? And that's why the second law isn't violated. So you read this in Wikipedia, and halfway down it says, in 1984, it was pointed out this argument is circular. But never mind. And you just carry on. Right. Okie dokie. This is an example of a wider problem, like Schrodinger's cat. It's in a superposition of dead and alive. Oh my goodness. That is just insane. The collapse of the wave function occurs when the radioactive atom occurs. The only reason for talking about something being a superposition of two states is if you can interfere them. And you can't do that with a cat, because it is not in a superposition of state. It's either dead or alive. Right? This is absolute gibberish. Schrodinger proposed this thing as an insane thing to show how wrong it was. Yet nowadays we think of cats being in states of dead and alive, etc., etc. Consciousness in quantum mechanics. We look forward to the day when consciousness will be included in quantum mechanics. Oh, yes. Since when was a quantum mechanical measurement made by a human being? When was the last time in science a measurement was made by anything other than a very simple machine with no consciousness? Yet we have to have consciousness. And anyway, if you disregard the notion there's something about human beings which transcends, isn't consciousness what you get if you connect a processor to a memory bank? To conclude, for science to advance, people need to understand what's been done already. And it seems to me in physics at least, this is the big problem we have. I know this is certainly true of my own experience. I did a degree in physics, got a decent result. Everyone thought I'd become a theorist, but I couldn't face it because I understood nothing. I knew I understood geometrically zero. So I went off, became an experimentalist, sat in a puddle of oil, and had a great time. But as the years went by, I taught physics, and I learned a little bit of physics. But we covered the material in the courses, but I didn't understand a thing. And I think that's very true of the way we've got to. So if you wish to do something which advances science, the lowest hanging fruit is to work out how to teach it better. Because then the next generation will have half a chance of doing something new. When my father was an undergraduate at Cambridge, and he ended up as a chemist and natural scientist, and he told me in my youth, relativity, oh, that's only understood by 12 people in the world. Now, okay, he did do chemistry, but the point is that was his perception in the 1950s. But that's not the case now. Every Tom, Dick, and Harry understands relativity, and in Cambridge, they teach general relativity in part 2, and the weakest students can understand it, I know as a DOS. They have got it nailed. The one subject which should be absolute nightmare, general relativity, every Part 2 student understands, because they've got it nailed. And it's partly because, and what you need in science is two geniuses. The first is the person who works out the original rules. And Maxwell, who did this, but the second genius is the one who works out how to explain it. And whoever thought of the light clock on top of a train was a complete genius, because it meant generations of students could understand relativity. So, in this context, here's to Maxwell. Because Maxwell was someone who both did the original work, and he had that genius for taking Faraday, who'd done this beautiful work on how magnetic fields produce electricity, but the guy didn't even know trigonometry. He couldn't even do trig. He was self-taught, had no education, yet he was a brilliant physicist, but he couldn't do the maths. Ampere, who worked out how you make magnetic fields from electricity, brilliant experimentalist, brilliant law, completely utterly unusable because it's so convoluted. And Maxwell had the genius to draw these together into a very simple form that people could use. So here's to Maxwell. It's the end of the day. Thank you, Claire. Here's to Claire for organising all this, and to the Philosophical Society. But I'd like to leave Maxwell with the last word. Now, I think Maxwell himself would have been probably pleased that 150 years later we're talking about what he did. But also I think he'd have a caveat. And the reason I think he'd have a caveat is because of his choice of the Cavendish motto. Now, it's quite singular what he did. Remember, this is not the Dark Ages, the Stone Ages, when he came up with this motto. But it was what Maxwell wanted to do. Now, let's have a look at this motto. So that's it in Paleo-Hebrew, it was written in that. The motto dates from about 1000 BC, probably one of the earliest ever statements about humankind as a scientist, which is perhaps why Maxwell chose it. Maxwell put it in Latin on the gates of the old Cavendish, and he used the words of the Vulgate translation, which was commissioned in 382 AD. Magnum opere Domini, exquisita in omnes voluntas eos. And over the Cavendish too, it's in English by that. And I think when people read this, many people would substitute the second noun for the word nature. But I think it expresses this universal feeling that human beings have, that there's something about us and what we do and science that transcends. And indeed, that's partly why you're here today, because it's something that there's something about this, basically. And his motto summarizes that. And so I think leaving with his take on things is probably appropriate. And we'll see what happens in Cavendish 3. Thank you very much.